Hello, and welcome to another video. Previously, I made this 1-bit adder with my son, and we kind of went through how the logic of it works to add two 1-bit numbers together in binary. And one thing we did was we had to do these pull-down resistors, which you need to keep the values from floating, right? So like, I'm still never quite clear on what values I should pick for these resistors, and I'm kind of curious as to why. And so I thought maybe I'll make a little video where I poke around a little and we see what happens, I guess. These ones in here are 1K resistors, and I kind of picked those arbitrarily. I've read a bit online about what values people use for pull-up and pull-down resistors in digital logic circuits, and it's usually, it seems like, it's pretty common to use something like 1K for pull down and 10K for pull up. I don't entirely know why those values are chosen specifically, but they seem to be pretty common in a lot of people's example circuits. The crazy thing is how many example circuits are out there that just do completely different things. They have completely different values. And that's true for these LED current resistors as well. It's like some of them use 330 and some use 220 and some use, you know, whatever they've got, I guess. I know it affects brightness, and I guess different colors need different resistors, but you know, I don't know the details on that. I don't know if that's standard that all colors have those, or if it's like certain manufacturers' colors need certain resistors. I don't know. That stuff's a bit of a mystery, and no one ever seems to quite say it on like tutorial websites. They're just like, use this one, you know, and but you can also use these four if you want to, you know, it doesn't matter. I don't know, you know, it's definitely hard to wrap your head around when everything's so vague. The chips switch and internally like switch between high and low, and their transistors switch based on, I think, voltage, and at least in the case of digital circuits. I gather sometimes, or maybe there's certain types of transistors that can switch based on the amount of current that comes in rather than the voltage, but I think for these it's always about voltage. And so what you really need is to change that voltage level somehow. So when a resistor is involved, like, it can change the voltage on one side or the other, right? So I thought, okay, why not just check it, right? I mean, we have a multimeter, we can just measure these things. So that's what I'm going to do. Volts. Now I know from the manual says that it fluctuates when there's no voltage at all. I guess it's essentially floating, probably, you know, maybe for similar reasons that you have to do the pull up and pull down on these logic circuits, actually. I got these neat little clippy thingies, and much better than the probes because you can clip stuff on. But I found that it was still hard to try and read voltage on here, so I figure I'll just use the clippy thingy to attach a wire to it that I can then poke into things. So we'll poke the common lead into minus, and we'll just leave that sit there. And the positive one, I'll put on a little probe, a probe, right? Okay, let's put that out of the way. So I think the first thing to do is I'll check, you know, the plus side, right? It reads 5 volts, almost exactly 5 volts. I mean, seems pretty accurate to me. I guess that's the voltage regulator doing its thing. If I put this on the minus, it of course reads nothing, because minus and minus. All right, so we have one switch off and one switch on. So if I check the off side, this one, the off switch, this means the current should be going through our pull down resistor, which is the one that's under, you know, right under the wire right here, this one. Okay, we can't see the multimeter now, but we can see the resistors. So this resistor is connected to this switch, and this resistor is connected to this switch, and these are these pull down resistors I was talking about. You see they connect to minus here. So there's 532-ish millivolts between ground and the other side of this pull down resistor. So it's a very small amount of voltage. But if we go to the other switch, the one that's on, we're getting close to 5 because it's not going through here at all. It's well, maybe a tiny amount is, but it's pretty much coming straight from plus. So this is our low signal, right? This is low. Now, that means it's close to 0. It's not actually 0. And that's kind of interesting to me because, you know, my software brain thinks in more absolute terms here. You know, this is 530 millivolts. It's not 0 volts. So how come this is still false? And apparently there are voltage ranges for what true and false is. And I guess you can find these kinds of things on the datasheet. So I am going to look up the XOR chips datasheet and see if I can find it and try and figure that out. This, I think, is actually the datasheet for this exact chip from this exact manufacturer. So that's pretty cool. When I've looked up some other chips before, sometimes I find similar ones by a different manufacturer, but it's like the same chip. It's compatible. I don't know how close these things are in between different manufacturers, but I'll just assume they're pretty close. Now, in this case, in this particular chip, it says it's an integrated 2-input XOR gate integrated circuit composed of 4 groups. Yes, okay, that sounds good. And has the logic drawn over here, like on the chip. That's kind of neat. So you can see here's VCC, here's ground, and we had hooked those up previously. And we use this gate on this side. So actually, I guess we use the last gate. I'm realizing now that the pin numbers actually go like this. For some reason, I had it in my head, you know, that they go down one side and down the other side, but they don't. They wrap around. What's this about? Absolute maximum rating. So VCC can handle 7 ratings. What does that mean? I guess they mean 7 volts, because the unit is volt. It can handle 7 of them. This seems remarkably obtuse in any case. Input voltage can be 7 volts. I guess that's probably the voltage on one of the pins, like the input. I guess input voltage is different from supply voltage. Operating temperature 0 to 70 Celsius. So I guess you can't boil this. But it can withstand a lot of cold and heat if it's not running, I guess. Okay, block diagram. Okay, that's just the logical symbol. Oh cool, like they have the truth table here. And that's like we were talking about before with, you know, logically. So if it's low and low, or, you know, false and false, the output's false. This is why it's an XOR, right? It's only exclusively OR when one or the other input is high. Those are the only 2 times that the output's high. Otherwise, everything is low. Okay, voltage. This is probably the stuff that I need to look at here. Okay, supply voltage. It says VCC's minimum is 4.75. Tippy must mean typical, I suppose, and then maximum 5.25. So it can handle between 4.75 and 5.25 volts and still function, I guess. And input voltage, okay, VIH. I assume that means the high, okay, voltage input high signal has to be at least 2 volts. The voltage input for a low signal, on the other hand, its maximum is 0.7. So 0.7 volts is false. It's not 0 volts, it's 0.7 or lower. This is probably the thing, I mean, almost certainly the thing that determines, okay, maybe not almost certainly, but I bet it plays a role in determining how big something like a pull-up or a pull-down resistor should be. Okay, so 536 millivolts across there, that's definitely less than 0.7 volts, so that means it's false. It's passing a, that counts as false. So I suspect then we can reduce the resistance and we would get a higher voltage across here, right? So I should be able to plop in a lower value resistor here, and maybe we can get near that 0.7 volts and see if the output changes. So let's try that. Okay, I have a 330 here because that was easy. I already had one cut and bent and stuff. So I'll just take out this, which I know is a 1K, and I'll insert the 330 if I can get my fingers to work correctly. Okay. Well, that was surprisingly difficult. Okay. So we have a 330 in here just on this number 1 side for now. So let me turn the power back on and see what we see. Okay, we're still seeing the right results. The meter says 186 millivolts. So that's like, isn't that 0.18? Isn't that below the threshold or not? 0.7 volts was the threshold, I'm pretty sure. Input voltage, 0.7 volts. 0.7 volts. 0.7 volts should be 700 millivolts, I think. This seems like that's lower than that. Oh, right. I'm totally thinking about this wrong. Of course lower than that is good. The lower it gets. But isn't this lower than what we had with the bigger resistor? It is, isn't it? Okay, yeah, it has more millivolts here. That doesn't match my expectation at all. Well, let's try an even bigger resistor then. Okay, that's a 100K resistor. And now it has 1.782 volts. That seems like a lot. Also, you can see now it's reading differently. It's reading as if both of these switches are on. Well, I don't understand the voltage situation, but when I take out the 1K and put back in the 330 or whatever it is that I've got here, that doesn't change anything. It's still technically correct here. So I guess what we'll do is we'll just go lower. I mean, my expectation with like a 10 ohm one is that it wouldn't block enough current, and so it should read as... Okay, I keep getting confused about this though, because there's a good chance that it's reading as very low anyway, because I mean that'd be kind of like not having this. Well, look at that though. When this is not connected at all, it's reading it as on. Because both of these have to be on for this LED to light up. That's the carry bit. So it's reading it as high. But nothing's but it's not connected. Yeah, it's reading it as on, the same as if number 2 was on, but it's not on. So why is that high? I don't know. So let's just put it here. Yeah, it's got 2 volts on it. So how does it have 2 volts on it? It's not connected to anything. This switch is off. This side is connected to nothing. So the only thing that's connected is, you know, to the gate's input here. And then that input is also connected here for the carry bit. The carry bit can only be on if both of these are on. So how are we getting 2 volts on a line that's not actually connected to anything? You know, it's not connected to plus anywhere. Yep, gotta say, this doesn't match my intuition at all, and I'm not actually sure where to go from here. I'm gonna have to... I don't know what I'm gonna have to do. How do you even search for this kind of a question? Resistors don't work the way you thought they did. How do you Google that one? But this is probably why I'm confused about a lot of things. Okay, it's been a few days since I recorded most of the previous stuff, and I had probably about an hour of footage of me randomly disconnecting and reconnecting things and being very confused about what I was seeing. And I managed to edit it down to like 14 minutes, so there's a lot of stuff I had to cut out about me being confused. And I never did quite unconfuse myself. I had to take a few days to read some stuff and watch some more videos about how electricity works. And I think I'm still pretty confused about it, to be honest. I think electricity is just maybe weird, but I never fully deciphered the pull up, pull down thing. I mean, I think there's an element of these values are chosen because they work because of, you know, physics and Ohm's law, but like, I sort of wanted more than that, you know, like I want a better intuition of it, and I don't have it yet. I think There's some analogies with water that make sense, and I'm pretty sure too earlier in the video I was maybe starting to conflate voltage and current, but they're of course very different things. Like current is the amount of electrons flowing, you know, past a certain point within like a second, and voltage is a potential difference, and it's more like pressure in some respects. It's a bit like water pressure, I guess, or like potential energy. Like you might remember, you know, physics problems where it's like the ball's sitting on top of the hill and it has some amount of energy even though it's not moving, and you know, you push the ball and then it turns to kinetic energy. And I think voltage is like the potential energy. It's just, it's not a force. It's just a measurement for those energy differences. And that's another thing too. Voltage is relative. So it really depends where you put your minus lead and your positive lead to determine what the voltage is, you know, because there isn't like, I don't think there's such a thing as an absolute voltage because it's defined as a relative, as a relation between 2 points. So anyway, I'm obviously still not completely clear on a lot of this stuff. The water analogy, I don't know if it actually helps with the pull-up, pull-down resistor thing exactly, but one thing I saw was suggesting things like, you know, imagine the electrical current is like a river, you know, and the water's flowing like downhill, right, down a gentle hill. If you were to put a dam somewhere in the middle of that hill, the water's going to start building up behind that dam, and it gets higher and higher and higher. Right, and if you have just a little hole in the bottom of the dam that the water's coming through, that dam acts like the resistor. And so what ends up happening is all this water builds up behind the dam and reaches a new level, and that new level is going to be higher than downstream, of course. So that means that that level of the water is the voltage, and the height of the water on this side versus the other side is voltage, right? That's essentially like maybe one way to think of it. And so the resistor is blocking most of the water from flowing, but it still lets, you know, some flow through, and the amount that's flowing there is your current. So I think I had things maybe backwards in my mind. When you have a large resistor, it's blocking a lot of current. So the trickle on the other side is smaller. That means more water on this side of the dam is going to build up and up and up and up, right? That means you get higher voltage on this side of the dam. For some reason, I was thinking larger resistor should mean less voltage, but it means less current, not voltage. And it makes sense, I think, when you start thinking about it like from a water and a dam point of view. So that's starting to kind of help me a little bit, but there's still other elements of electricity that are just, they hurt my head. There's, you know, an electromagnetic component to electricity too. So like electrons move in the wires, but then of course things like transformers work even though the two sets of wire coils don't actually touch each other. And that's because of the electromagnetic currents being induced. And I'm pretty sure that the electromagnetic currents, or the electromagnetic fields, are probably what's responsible for the floating voltages and stuff that I was seeing. And that might actually be partly to blame for the floating concept entirely. Right, like current's moving nearby, and it's inducing an electric current in pathways inside the chip and possibly in the wires that you didn't really want. And that shows up on these wires that aren't even connected. And that is just maybe what we call floating. That sort of makes sense, because otherwise I think there's a lot of stuff that just wouldn't work in the world. You know, like electromagnets wouldn't work and electric motors wouldn't work. You know, the relationship between the fields and the movement of the electrons is probably why floating exists in the first place. And presumably you use things like the pull downs and the pull ups to put, you know, a much higher voltage on those lines that are maybe disconnected so that it, you know, it has a voltage that you want it to have rather than just whatever it happens to pick up from the environment. I think that's kind of the general gist as to how to choose the values, which is what started the whole video in the first place. I still don't 100% know, but it probably is. It probably matters how much current is being drawn, right? Because putting in those smaller resistors cause the voltage to go down closer to 0 in the case of these pull down voltage or pull down resistors. And of course, I was thinking I want to optimize for that, get the lowest possible voltage level so that it's as close to false as possible, that would be the best thing to do. But what I wasn't measuring and thinking about was that a lower resistor means more current is going to flow. And current is, your energy usage, right? So like if this wasn't a power supply but was instead a battery that could run out, you could have a really small resistor here as your pull down resistor, except a bunch of current would be flowing across there all the time, and that resistor would eventually, get hot, and it's wasting a lot of energy, and you don't want that. So I suspect part of the calculation there for determining optimal values for the pull-ups and pull-downs are things like computing how much current is flowing in those states, because you probably want to minimize that to save energy, especially if you're running off of a battery or building a fancy cell phone that's supposed to last all day or something like that. Obviously, I have no idea how to compute all that stuff, but I'm sure it has a lot to do with Ohm's law, and it's like knowable, but I don't have an intuition for it yet, I guess. And so anyway, that's where I'm at. I was gonna try to come up with some grand explanation at the end of all this and tie it together and make myself look super smart, but I think I don't know enough to be able to do that yet. So I'm just going to end it like this, and hopefully we'll learn more later. So that's it for now, I guess. You could thumb up this video if you want, and subscribe if you like. And I don't know why. I mean, I was confused the whole time and you probably didn't learn anything. I'm not sure if I did either, but that's it for now. Bye.